that I find it almost impossible to imagine. Well, actually impossible to imagine. One's just the size and scale of it. I mean, in the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion, 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it. It is impossible to visualize the scale of the universe. Well, we'll stop there for now, but just the size and scale of it, I think, is beyond imagination. So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. And it answers some neat questions, because if you say, why is our universe the way that it is? Why are the laws of nature such that life can exist, for example? Well, the answer might be that all possible combinations of all the laws of nature exist in the inflationary multiverse. So then it's not surprising there are universes that permits things like us to exist, because every possible universe exists in the inflationary multiverse. And that's a well-supported theory. It's a theory, so this is not the same as saying there was a Big Bang, which we know. This is kind of, what's a theory? It's a guess, basically. But it is a theory that in its simplest form has made predictions that have subsequently been verified. And we could go on then. There's the so-called many worlds interpretation of quantum mechanics, which is more kind of Marvel film kind of multiverse, where so quantum mechanics it's a probabilistic theory. So imagine a quantum coin, I call it. And the quantum coin it doesn't have to be heads or tails, it can be heads and tails. So it can be mixed up, it can be both heads and tails at the same time. You may have heard of Schrodinger's cat, which is a cat in a box, and it's both alive and dead until you observe it or interact with it in some way, and then you find out which one it is. But before you looked at it, or before you interacted with it, it was both. I say sometimes in my live shows, it's kind of a joke, right? So I'm not insulting philosophers here, but I say there's only one interesting question in philosophy. And I don't really mean it, but I think it sounds funny. So the interesting question is, what does it mean to live a finite, fragile life in an infinite, eternal universe? So that's not that funny, right? It's a good question. What does it mean to live a finite, fragile life in an infinite, eternal universe? And I think the answer is that sort of paradoxically, whilst we are definitely physically insignificant, we've just said that the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of the universe, right? So we're definitely small, and you can't argue with that. We're just specks of dust. But if you think about what we are, so everybody, me and you, everybody, we're just collections of atoms, right? Some of them are as old as time, pretty much, and some of them were the other ones. Everything else, other than the hydrogen in our bodies, was made in stars, right? So we're all cooked over billions of years. Now, as of 2019, I would say, we think that if you think of yourself as information, so if you think of let's say, think very 2022, right? Let's say you burn a book. We're very fashionable current political climate. So burn a book and collect everything that comes out of the book, all the ashes and all the gas and everything. Then in principle, you can reconstruct the book. Not in practice, right? But you can imagine if you collect every single thing and measure it, in principle, you can reconstruct the book. Information is conserved in all of physics, which means that, so basically, if you can measure everything perfectly, you can predict what happened in the past and what's going to happen in the future. It's called determinism, that, right? So the old picture of black holes, and Stephen Hawking believed this for a long time, had a bet about it actually, is that they seem like they destroy information. You can kind of see it goes to the end of time, right? It's gone. And then they evaporate away, and it seemed that there was no way, even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it. But now we think, actually, no, even black holes don't destroy information. So it turns out that now we think, and this is very 2022 papers, right? If you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out. Stephen Hawking had a bet with John Preskill about this. So, and it was, I can't remember, I think it was the 90s when he conceded the bet. It might have been the late 80s. But so he had a bet, and the bet was that Stephen's calculation initially from the 70s said that black holes destroy information. And so he thought that was true for a long time. And he had a bet with John Preskill. And it turned out that the bet was a set of encyclopedias. So whoever lost the bet would have to give the other one a set of encyclopedias. And John Preskill asked for baseball encyclopedias. And because of some work by someone called Maldacena, actually, ultimately, Stephen said, no, they don't destroy information. The information comes out. It's conserved. So he conceded the bet and gave John Preskill the encyclopedias. He said, what I should have done is I should have burnt the encyclopedias and given him the ashes. The possibility is that we discussed we could destroy ourselves, which is, it would be, given that it's quite possible that there is nowhere else in a galaxy, then, as we said before, that would be a really silly thing to do. So I think it's more likely, we might not have to wait for the sun to do it, because we might do it through our own stupidity.
Even very simple things, like you go back to the Greeks, so Aristotle, and there's great, very clever people, but they thought the Earth was at the centre of the universe. Why? Because it feels like it. It feels like we're not moving. And that's quite a deep point, actually, in physics. It's like, why is it that we're flying around relative to the sun very fast at whatever speed it is, 18 miles a second or something like that, and the whole solar system is going around the Milky Way galaxy and so on? Why is it that we don't feel it? And the Greeks quite naturally said, well, because we're at the centre of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the centre. It's natural. And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. And he said, well, there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space. So if we think about space, if I said space to you or most people, I suppose, you'd think it the way that Newton did, of a big box within which things happen. And that's got to be, that's a natural picture of space and the universe, isn't it? It's a thing in which all the planets and galaxies are placed. But in the Brief History of Time, Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective, but from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. And then from some other perspective, it would have done something else. So the point is, you can't say this is a point in space. It came back to the same place, because that just depends on your perspective. It depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space.
Before we start thinking, by the way, about going out to the asteroids and mining them and building cities on Mars and building cities on the moon and so on. But let's just talk about Earth orbit first. It's tremendously exciting, huge opportunity. But of course, when you start to move outwards to a new frontier, then the frontier can become crowded. You can have competition for the real estate. You need some way of managing conflicts between, by which I mean physical conflicts between the satellites. What happens if someone's satellite comes close to another satellite? How do you manage that? Do you allocate particular orbits? Or do you say that we're going to have some framework like air traffic control, where you have an avoidance system that everybody agrees on, whereas if two things come close, they avoid each other? That framework is not yet there. I attended several meetings and conferences where there are, of course, many countries and international bodies that are trying to work on the management of space. I find that it's a challenge because of course, it's always a challenge when different countries and different commercial interests and so on are trying to flesh out agreements about how you manage a frontier. But ultimately, I find it exciting. Because what it means is we're now at the stage where, as the great Carl Sagan said, we're beginning to take our first steps out into the cosmic ocean. And I always remember, and he said, the water seems inviting. So it's a tremendous opportunity. But what kind of opportunities are going to open up? Well, we know, for example, so already from our experience on the International Space Station, that sort of development of new drugs, for example, or development of new ways of building semiconductors, for example, silicon wafers and so on. Lots of experiments have been done that suggest that there might be an advantage to on-orbit manufacturing. So it's in a microgravity environment of certain things, growing crystals and so on, which might be useful. And so as we begin to get more experience operating in microgravity, we begin to see that there are applications for particularly material science and biosciences. But beyond that, so when we start to move outwards beyond near-Earth orbit and build the infrastructure that we need close to the planet to begin to move further out into space, then opportunities begin to open up that I find tremendously exciting. So one very well-known example would be mining asteroids. So one could argue, there are people that argue, that one of the biggest problems we face and have faced historically on Earth is competition for resources. So not only just the pure competition, which leads to conflict and war, if you think those resources are limited, which they are on Earth, but also just the stress, of course, that you put on the Earth itself, on the environment, as our civilization grows and requires access to more resources. It damages the planet, it creates conflicts and so on. But if you have the infrastructure to begin to move outwards, for example, to the near-Earth asteroids, then what you find is that resources are no longer limited in any reasonable sense. There are vast amounts of resources out there in space that we will have access to within the next decade or so, or certainly few decades, which you're forced to do when you think about the distance scales and the sheer size and age of the universe. Then I think it's very natural for us to tend to come to the conclusion that we don't matter at all. And it is true in some sense, just physically. What are we? We're little specks of just a collection of atoms on one mote of dust orbiting around one little star in 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of a potentially infinite universe. So clearly it is true. We are physically insignificant. So I've tended in the past to focus arguments or think about arguments of our value in the context of what does it mean to live these finite, fragile lives in this infinite universe. And I could make a strong argument, and have many times, that notwithstanding our physical insignificance, we may be remarkably valuable, because the number of civilizations on the average in a particular galaxy, any given galaxy, might be less than one on the average. Many galaxies may not even have civilizations in them. If that is the case, and that it's speculative, but if it's the case, then we would be remarkably valuable, notwithstanding our physical insignificance, because we would be perhaps the only place in the Milky Way galaxy where collections of atoms have come together that can think and do science and have conversations like this, in a very real sense, bring meaning to an otherwise meaningless galaxy. So that has been my position for some time. I think it's a good working hypothesis, by the way, as an aside. If you think that I think Carl Sagan said it many years ago, in some sense, if that's the case, we have a responsibility to the cosmos itself. Because we're a product of 13.8 billion years of cosmic evolution, but we might be a very rare and special product. But we might only be here. We'll only be here for a small amount of time. The sun will only be here for a small amount of time in cosmic timescales and so on. So I've tended to make that argument. But one of the great joys about reading other people's views about essentially being a scientist is that you can come across a point of view and you think, I haven't thought of that I might change my mind given that wonderful piece of thought. And I found it happened to me recently. I was reading a book, it's a very old book now, by David Deutsch, who's one of the greats, one of the founders of quantum computing. So he's really is a physicist and a thinker worth paying attention to. And he made a point, which I had heard before actually, in a book called The Anthropic Cosmological Principle by John Barrow and Frank Tipler, which is a huge influence on me when I was an undergraduate physicist, so I couldn't believe I'd forgotten this point. But David Deutsch and Barrow and Tipler pointed out that it's not necessarily the case that life will always be a speck, right? Something that's very valuable and local in the universe, but doesn't make much difference on a cosmic scale. It's not necessarily the case, because you can imagine, so let's take the Earth as an example. So you might say, well, a planet is a very big thing and living things are very small, so they don't make much difference to a planet. That's wrong, because if you look at the Earth, its atmosphere is the product of life. It's got oxygen in it in high concentration. It would not have that without photosynthesis. So obviously now, our civilization has sculpted the surface of the Earth. You see it. If you look at the Earth from space, you don't just see oceans, you don't just see a kind of common or garden planet. On the night side of the planet, you see our civilization. So we have now transformed the Earth as a civilization, but life has been transforming it for billions of years. So you could say, well, okay, so what happens if we stay here? We become a spacefaring civilization. We don't destroy ourselves, or we aren't destroyed by some impact from space. Then could you conceive of technology that could start to affect the solar system? And the answer must be yes. We could imagine building cities on Mars. We could imagine, in physics, pure physics terms, terraforming Mars, turning it into a habitable world. We could imagine going to the moons of Jupiter or Saturn. We could imagine going to the edge of the solar system. You could even imagine, could you imagine technology in 1 million years, let's say, that would allow us to begin to affect the lifetime of the sun? Could you imagine that? In physics terms, according to laws of physics, I suppose you could. You could imagine a tremendously powerful civilization that could start to, I don't know, throw material into the sun, whatever it is. Maybe it was a ridiculous thing to do, but you could at least imagine it. And then you go 1 million years, 2 million years, 3 million years, 10 million years, 1 billion years into the future. Imagine that our civilization expands to the stars.